Hello, so today I'm going to be talking about Hindu mathematics, specifically from the 6th century to 1600. And this was such a wide time period. So many mathematical developments and advancements were made. So I'm going to throw a bunch of math at you, but to structure it a little bit better, I decided to go through chronologically the major mathematicians of the time through this time period and what their major accomplishments were and what their contributions were to mathematics. Specifically, a lot of advancements were being made in arithmetic, algebra, geometry, calculus, and trigonometry. So first, I'm going to start off with just a bit of historical information to kind of give you a background of what's going around or what's going on in India simultaneously to all of these mathematical advancements. So the 6th century began with the end of the Gupta period, and this was really a huge time for cultural flourishing. Like there was the emergence of mathematics, veterinary science, medicine, astronomy, astrology, and astrophysics. And they had a very strong central government, which was good because it created a lot of peace and prosperity, which promoted all of that, the pursuit of science and art and math. So yes, there was a very strong government, allowed for lots of control, and society was run under Hindu beliefs. And so as time went on, there was the collapse of empires, and it caused power to become very decentralized in India. So we were ending the Gupta period in the 6th century, and then that empires were falling and rising over time, and it created a lot of chaos. The smaller kingdoms became very dependent on larger kingdoms. We have feudalism, lots of religious rivalry. So Buddhism and Hinduism were the two main religions in India. And with the rise and fall of empires and the religious rivalry, Buddhism began to decline, and Hinduism faced a lot of military violence. But because of these shifts in power, it allowed for the constant spread and development of mathematics, literature, science, art, etc. So I'm going to start by talking, and I'm sorry if I butcher this name, probably going to do that a lot throughout this presentation, but we have Aryabhata, and I know somebody else is specifically doing a presentation on him, so I'm just going to do a quick run through of what he did, but he had some major mathematical advancements in the beginning of the 6th century. So he had contributions to the place value system and zero. So it's argued that he used zero as a placeholder for the powers of 10 in null coefficients. And he used letters from the alphabet to denote numbers and express quantities. He also approximated pi accurately to 3 decimal places. And as we go on throughout time, we're going to actually see that pi is being calculated more accurately to more decimal places as we go on. So I think that's also kind of an interesting to look at whenever we're observing such a huge time frame. We can kind of see the improvements that are made about certain mathematical properties as we go along. He also developed the method that became standard for solving first-order Diophantine equations and provided results for summation of series of squares and cubes. So this first series right here is the sum of squares, and so we should be familiar with that. That's kind of what we use today. The second one is the sum of cubes, and so this may look a little bit different than what we're used to seeing. So we're used to seeing n times n plus 1 over 2 all squared. But either way, we get the same answer if we plug in values for n. This is kind of just what he discovered back in the day, and that's kind of how he formed that to look like. Moving on, we're going to talk about Varahamihira, who was born in 505 and died in 587. And so he has 2 main works that he had. I'm not even going to try to pronounce those, but you can look at those names there. So the very first one, this one right here, the Pancha, again, not going to try to pronounce that. This was a treatise on mathematical astronomy, and it summarizes 5 earlier astronomical treatises by 5 other authors. but those 5 treaties by the other authors were lost. And so this treaty created by Varahamihira is it gives information about those older texts that are now lost. So we have all that information in this treaty now. And so this second one right here, his second work, this is an encyclopedia that covers a huge wide range of subjects, particularly relating to human interest. So this encyclopedia talks about things like astronomy, planetary movements, eclipses, rainfall, clouds, architecture, growth of crops, manufacture of perfume, matrimony, domestic relations, gems, pearls, and rituals. Again, just a huge range of stuff in there. He made some major contributions to trigonometry. So he improved the accuracy of Aryabhata's sine tables to 4 decimal places. And this is, again, something else that we're going to see is improved upon over time, the sine tables. And he discovered the following trigonometric relations. So we actually use these today. They should be familiar. We have the sine squared x plus cosine squared x is equal to 1. Sine of x is equal to cosine of pi over 2 minus x. And 1 minus cosine 2x over 2 is equal to sine squared of x. All right, so now we're going to move on to Brahmagupta, who is actually one of the more famous mathematicians of this time period. He was born in 598 and died in 668. And his main work is that really long, ridiculous word right there. So I'm going to be referencing that as I talk about Brahmagupta, and I'm just going to say his main work, and I'll be referencing that really, really long word right there. So Brahmagupta actually had so many mathematical discoveries. So I included the main ones in here. The first one I'm going to talk about is his theorem. So it says, if a cyclic quadrilateral has diagonals that are perpendicular to each other, then the perpendicular line drawn from the point of intersection of the diagonals to any side of the quadrilateral will always bisect the opposite side. So we're actually going to prove that now. So we need to prove that AF is equal to FD. So we want to prove that this line right here, this blue line, bisects this line segment AD. And so we'll prove this by showing that AF and FD are both equal to FM. So to prove, first we're going to prove that AF is equal to FM. So we can see that the angles FAM and CBM are equal because they are inscribed angles that interact or intercept the same arc of the circle. We can also see that CBM and CME are complementary. So they add up to 90, and therefore they're equal. And then we can see that CME and FMA are the same. So we can see that AFM forms an isosceles triangle. And so from that, it follows that AF and FM are equal. We could do the same to prove that FD is equal to FM. And so again, by the same that we did above, we could see that FDM, BCM, BME, and DMF are all equal. So we have that DFM is an isosceles triangle. And then from that, we can see that FD and FM are equal. And so from that, it follows that AF and FD are equal as the theorem claims. Continuing on with Brahmagupta's work, we're going to move into algebra. So he gave the solution to the general linear equation. So the solution is x is equal to e minus c over b minus d. For the equation bx plus c is equal to dx plus e. He also gave 2 equivalent solutions to the general quadratic equation. So I have both of those shown there. And if you look at those, you can see they're really similar to the quadratic equation that we use today. Again, a little bit different. And he was able to come up with 2 equivalent solutions. So that's kind of cool. Next, we have Brahmagupta's formula. So it says the area A of a cyclic quadrilateral with side lengths A, B, C, and D is that formula right there. So we have A is equal to the square root of S minus A times S minus B times S minus C times S minus D, where S is the semi-perimeter given by A plus B plus C plus D all over 2. And so using both of those things, we can find the area of this cyclic quadrilateral. And then again, just a couple more things that Brahmagupta accomplished mathematically. He did a lot of work with arithmetic. And his text, again, that really big long word that I couldn't pronounce, is the earliest known text to treat 0 as a real number rather than a placeholder. And he actually describes the operations on negative numbers. So the following 4 little snippets below are all from his text. And they each give descriptions of the operations on negative numbers. So the first one says that the sum of 2 positives is positive, sum of 2 negatives is negative, the sum of a positive and a negative is going to be their difference. And then if we have the sum of 2 equal positive negative numbers, we're going to get 0. And then he includes 0 in here also. So the sum of a negative number and 0 is negative. The sum of a positive and a 0 is positive. And then the sum of 2 zeros is 0. The next he talks about subtraction. So a negative minus 0 is negative. A positive minus 0 is positive. And then 0 minus 0 is 0. And then when a positive is to be subtracted from a negative or a negative from a positive, then it's the same as saying that we're going to add those. And then the product of a negative and a positive is negative. The product of 2 negatives is positive. The product of 2 positives is positive. And then the product of a 0 and a negative, a 0 and a positive, or 2 zeros is all going to be 0. And then finally, talked about division. So a positive divided by a positive or a negative divided by a negative are both going to be positive. 0 divided by a 0 is always 0. A positive divided by a negative is negative, and a negative divided by a positive is also negative. So it's kind of interesting to see that this is finally being formulated, these operations, because as we know, negatives and zeros are kind of they're not fun to work with, especially back then. A lot of people were scared of that. And so these were some of Brahmagupta's major mathematical developments. I didn't incorporate everything that he did because, like I said, there's a lot. But some other things that he did was he made progress in finding integral solutions of Pell's equation, along with some contributions to the Pythagorean triplets and the sine table. Again, like I said, those contributions to the sine tables are going to continue to happen throughout this time period. It's going to get more accurate. But again, for the sake of time, I didn't want to include all of that. Again, if you look at all his work as a whole, it's very, very overwhelming because he was very famous and he did a lot of mathematical calculations. So we're moving on to Bhaskara the First, and I'm going to make that distinction now because we're going to talk about Bhaskara the Second later on. So Bhaskara the First was born in 600 and died in 680, and he's credited to be the first to write numbers in the Hindu-Arabic decimal system with a circle for the 0. And so before this, numbers were represented in words or allegories. So before Bhaskara started writing numbers in the decimal system, numbers were represented, like I said, by words or allegories. So the number 1 would have been represented by something like the moon. Number 2 would have been represented by wings or eyes, because those come in pairs. And then number 5 probably would have been represented by 5 senses. But with this discovery, they started using writing numbers in the Hindu-Arabic decimal system. Let's see, Bhaskara also gave an approximation formula for sine of x, and it had a relative error of less than 1.9%. So you can see that formula there. If sine of x is approximately equal to 16x times pi minus x over 5 pi squared minus 4x times pi minus x, and x has to be in between 0 and pi. Alrighty, we're going to move on to Mahavira, and he's a 19th century or a 9th century mathematician. I tried to find when he was born and when he died, but for some reason that information doesn't exist. So we do know that he is a 9th century mathematician though. And he gave systematic rules for expressing a fraction as the sum of unit fractions. So I'm just going to give a couple of examples because he came up with a ton of formulas. I'm not, again, for the sake of time, not going to include all of those. So here's just a couple. So he found out that he can express 1 as the sum of n unit fractions, and he expressed it in that formula there. And then he also expressed a unit fraction as a sum of 2 other unit fractions. Again, that is shown there, and p must be a multiple of n minus 1. And then again, I kind of just included that picture off to the side right there. So that's a sculpture of Mahavira. And I just thought it was very important to include a sculpture because during this time, sculptures were a very popular thing in art. They like to make sculptures to represent their gods. So they also would like to make sculptures of their mathematicians who they highly respected and valued. So we're going to move on now. He also discovered algebraic identities like a cubed, which is equal to a times a plus b times a minus b plus b squared times a minus b plus b cubed. And he approximated the area and perimeters of ellipses. He claimed that the square root of negative numbers does not exist. Again, like I said, we know that negative numbers were kind of a scary thing back then, especially the square root of them. So Mahavira claimed that they just did not exist. And then I just have next listed a couple of things that he was able to solve. So he solved cubic equations, quartic equations, some quintic equations, along with indeterminate, quadratic, cubic, and higher order equations. Next, we have Sridhara, who was born in 870 and died in 930. He had 2 main treaties. I'm not going to say the names again. I'm very bad at pronouncing things. I don't want to butcher them at all. So again, 2 main treaties. And a lot of these mathematicians had treaties, and they put all of their work into these treaties so that they could be documented over time. And so Sridhara gave an exposition on 0. So this is very similar to what we saw with Brahmagupta. So it says if 0 is added to any number, the sum is the same number. If 0 is subtracted from any number, the number remains unchanged. And if 0 is multiplied by a number, the product is 0. So again, this idea of 0 is becoming very important during this time period in this area with Hindu mathematics. He also found that for dividing fractions, we have to multiply the fraction by the reciprocal of the divisor. So that's something that we do in elementary and middle school. So he actually figured that out also. He provided a good rule for finding the volume of a sphere. And he also gave a formula for solving quadratic equations. Again, for the sake of time, I'm not going to go into too much depth on each of these things. I kind of just wanted to give an introduction into what each person was doing at each time frame throughout this entire time period. And alrighty, moving on. So now we have, again, probably going to butcher the name. We have Aryabhata II this time, who was born in 920 and died in 1000. And he is a mathematician and an astronomer. And I made sure to include an astronomer in there because he was very, very, very involved with that. And I'm actually going to include some of that in this slide. His most famous work is listed right there. Again, most of these mathematicians documented all of their work. So his work had 18 chapters, and 12 of which were dedicated to mathematical astronomy. He liked to use geometry, geography, and algebra to calculate the longitude of planets. And he played a vital role in constructing a sign table accurate to 5 decimal places. So we saw earlier that we could construct a sign table accurate to 4 decimal places, and now because of Aryabhata II, we are able to calculate it to 5 decimal places at this point in time. And then he also gives rules to solve the indeterminate equation by minus or is equal to ax plus c. And so his rules actually apply to a bunch of different cases. And some of those cases were when C is a positive value, when C is a negative number, when the number of quotients is an even number, and when the number of quotients is an odd number. So he was able to solve the indeterminate equation for those different cases. And then now we've got Bhaskara II, who was born in 1114 and died in 1185. And he's particularly known for discovering the principles of differential calculus. And he was thought to be the first to come up with the differential coefficient. So he gave the result that if x is approximately equal to y, then sine of y minus sine of x is approximately equal to y minus x times cosine of y. So he was able to find the derivative of sine, even though he hadn't really developed the notion of derivatives at that time. And he understood that as a variable approaches the maximum value, its differential disappears. He was also an astronomer, like most of the mathematicians during this time frame were, and he calculated the length of the Earth's revolution around the sun to 9 decimal places. And so finally, I'm going to talk about Kerala mathematics. So this is the final period of this presentation. So from 1300 to 1600. And so Kerala, South India was a very, very, very popular area for mathematics and astronomy. So I have a picture right here. That yellow area is Kerala. And they had a school, the Kerala School of Astronomy and Mathematics. And there were so many contributions to calc specifically. So the most important result was series expansion of trig functions. And so you can see those listed there. And then I'm going to compare those to like what you see on the screen right now to what we know today in calc. But before that, I want to mention that Kerala was in continuous contact with China, Arabia, and Europe. So there was so much trade going on during this time. And the knowledge of all these mathematical results were spread through that trade. So moving on. So considering those examples we just looked at, whenever r is equal to 1, those expansions would reduce to what we recognize today as the standard power series. So we have sine of x and cosine of x, and we remember those from calc. So if I go back a slide, these expansions right here are the same as the ones we use today. They just use an r. And the reason for that being that the Kerala school did not use the factorial system. So that's why their expansions did not look like this. They looked a lot more complicated. So they used that r there. That's kind of what makes it look really, really complicated. But now, because we use factorials, we're able to simplify that a little bit. And so we understand it more today, and we use that in calc. We also, our Kerala mathematics, the school was also able to express the arctangent of x to get the infinite series expression for pi. So we see that there. And this was very important because they were able to use it to calculate pi correct up to 9 decimal places. So here we are again, calculating pi in a more accurate way. So we went from calculating pi to 3 or 4 accurate decimal places at the beginning of this time period to now having it correct up to 9 decimal places. And so that's going to be it for this time period. Again, we saw so much math happen, advancements in arithmetic, algebra, geometry, calculus, trigonometry, a lot of astronomy also. And there were very many mathematicians over time who contributed a ton of work and improved and expanded on what was already known over time. And a lot of that we still use today, like we see right now with the calculus. So this was very, very important to mathematics and what we know today. And so there are my sources. Thank you so much.